Hi everyone, so the goal of this video is to understand momentum and collisions. Specifically, your learning target is to describe momentum, explain conservation of momentum, and calculate the momentum of an object. Now that could be a simple object moving, or that could be an object that has gone through some kind of collision. We'll talk about that as we get through these slides. So as usual, before we start, find a good spot in the classroom or wherever you are so you can focus on the video. Make sure you have a copy of the guided notes, and the use of headphones is suggested. And as usual, there's a little tip on the bottom of the screen there. You can change the playback speed if I'm talking too fast or too slow. Use the playback speed button to adjust the settings. All right, so what is momentum? So we commonly hear the term momentum in everyday life. We might use it in sports. We might say, oh, the Steelers have won their last 3 games and have a lot of momentum. We can talk about a team having a lot of momentum in the game. Like, oh, the momentum has shifted in favor of the Yankees or whatever team you're talking about. We even hear teachers say it, like, "Oh, keep it up, keep working. You have great momentum right now. You know, finish the quarter strong. Your grade looks great, whatever." So momentum is all about being kind of hard to stop. And in physics, we use a very similar definition. In physics, momentum is commonly defined as mass in motion. And it really just comes down to your mass and your velocity. And you're multiplying those two things to find your momentum. And then this little clip I have here, this is a running back. Back in my day, there's a running back named Jerome Bettis. And he was nicknamed the Bus because he was very hard to stop. He was a big man, but he also could run very fast. So that combination of mass and velocity made him a very good running back. And as you can see, he was very hard to tackle. He was very hard to stop. So momentum is mass times velocity, or sometimes we'll abbreviate that as P equals M times V. So the first thing I'll say is yes, P is the symbol for momentum. That can be annoying, but M was already taken. We use that symbol a lot for other things. M was taken. You can try to think about other letters that might be useful, but we settled on P, and there's a lot of backstory behind that, but that's just the way it is. Other things, the units for momentum are kilograms times meters per second. That's also kind of clunky. Sometimes we have nice units like newtons, and it's just like one word, and it's very simple. This is kilogram meter per second, which is not the easiest thing to say, but as you can see, this is the unit for mass, this is the unit for velocity, and we're just multiplying those two things, and that's our unit. Momentum is a vector quantity, so keep track of which direction an object is moving. Because momentum is a vector quantity, it can be negative, and you need to keep track of which direction is it moving, left, right, east, west, whatever term is used in the problem that you're given. All right, so here's a quick little practice problem, and maybe I'll just put the answer somewhere on the screen here. So we have a cart that's going 5 meters per second, and let's say that the cart has a mass of 3 kilograms. So I could say that momentum is mass times velocity, and I can plug in those numbers. So I could say 3 times 5, and so that leaves me with 15 kilogram meter per second. That's pretty much it. So anytime you're asked for the momentum of an object, you want to take mass times velocity. All right, here's one for you, and I'll probably have a moment here where you have to stop the video and answer this question. What is the momentum of a 2 kilogram cart moving at 8 meters per second? Try to answer that question on your own. All right, so here I have a bunch of equations at the bottom of the screen, and I'll break down what these equations mean. But what these equations really mean, and one major idea here, is the conservation of momentum. So when two objects collide, their momentum is conserved. What exactly does that mean? Well, it means that the total momentum of the system before the collision will be exactly the same as the momentum after the collision. So you could have two objects that collide, And whatever their momentum was together before the collision will be equal to whatever their momentum is after the collision. And that's actually a pretty interesting phenomenon that happens when two objects hit. And it can be really useful to know that, right? If there was a car accident and two cars collided, and you don't know all the information, but you kind of have an idea of how fast one car was going and how fast another car might have been going, and you know the masses of both cars, you can make a pretty good, reconstruction in your head about what caused the accident, maybe who was at fault in the accident. So that's a pretty powerful equation that can be used in many different ways. So with this equation, well, there's two equations here. The first one basically says the momentum of object A plus the momentum of object B before the collision is going to be equal to the momentum of object A and the momentum of object B after the collision. So we use A and B and maybe some other letters to describe which object are we talking about. And then you might notice these little things, these little apostrophes. We might use those to describe the same object, but just after the collision. Another way to say that, right? This P stands for momentum, and momentum is mass times velocity. So this longer equation pretty much just breaks down this other one into its mass and velocity for each object. So again, the mass and the velocity of object A plus the mass and velocity of object B before the collision is going to be equal to the mass and velocity of object A and the mass and velocity of object B after the collision. And so, like I said before, if you know the masses that are involved in the collision, and you know maybe the velocity before the collision, you can maybe predict what's going to be the velocity after the collision. Or, whatever information you're missing, if you have some of these other variables, you can find your missing variable, and you can figure out what happened in the past if you knew what happens, maybe after an accident or something like that. So we will be using this equation. I will have you practice using this equation. And a key idea is that the momentum before is going to be equal to the momentum after. So there shouldn't be any change in momentum. And so if you're working on any kind of problems and you find an answer where the momentum is higher before or higher after, you might want to check your math. All right, and the last thing I'll say, like I said, this has a lot of real world implications. When we talk about car safety, when we talk about collisions, we talk about helmet to helmet collisions in football, or really any kind of collisions in football. And I'm sure there's many other examples, right? This idea of momentum is a very important measurement. And actually, maybe one of the last things that we'll talk about before the end of this unit is another idea called impulse. But basically, this idea of collisions and impulse and force, it's a really important concept. And there's been a lot of changes in our society, especially in football, or changes in cars over time, to kind of reduce the force in a collision, or reduce the change in momentum in a collision. And it's all about protecting people. It could be saving lives in a car accident. It could be saving a football player's life with better helmet technology. So there's a lot of real world implications, and we're always trying to improve these things depending on what we're looking at. So take that with you, and you probably have a few things to do, maybe a few practice problems, maybe a simulation to play around with. So remember to use that equation, use the conservation of momentum equation, and that's it. Good luck.